Okay, we're going to go over some more problems from page 21. So we're looking at Lewis dot structures. Remember, our first step with Lewis dot structures is to add up the number of valence electrons. So carbon is 4, and there's 2 of them, and then I've got 3 hydrogens and 1 fluorine. So that is 8 plus 10. So there are 18 electrons in this picture. I'm going to put the least electronegative element in the middle. It looks like there's a tie here. There's 2 carbons. They're each the least electronegative. And then I'm going to put the other elements on the outside. And I could choose to put 3 H's on one side and 1 F on the other, but I'm going to err on the side of symmetry. That's always a good first guess, and we could always revise it later. So I connected everything with single bonds. My next step is I'm going to give my outer atoms an octet. My hydrogens only need 2 electrons, so they're good. So I'm just going to give fluorine an octet. And then my next step is to put all the extra electrons on the central atom. So I have to stop and count and figure out how many extra electrons I have. So I've used up 2, 4, 6, 8, 10, 12, 14, 16. That means I've got 2 left over. So I'm going to put them right here. And then I'm going to check and say, do I have an octet? So is everyone happy here? And nope, this carbon does not have an octet. I have no more electrons left to give it. So that is my clue that I need to form a double bond. So I'm going to take this pair of electrons right here that carbon is hogging all to himself and make that carbon share them. So I still have 18 dots. So that's what you want to check for, how many dots. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's good. Boom. And then everyone has an octet around it. Perfect. So my Lewis dot structure is good. It also can be a good habit to check the formal charge, which we'll go over finding the formal charge in a minute. All right, let's look at BCl3. Again, count your electrons. So boron has just 3 electrons around it, and then we got 7 from each of the chlorines, so we're going to have 24 electrons here. So boron goes in the middle because it's the least electronegative. I'm going to start by attaching things to it with single bonds. I'm going to give my outer elements an octet, and then I'm going to put any leftovers on the central atom. So let's see how many leftovers we have. So we start out with 24, and it looks like we've used up 24 electrons. So I've got no leftover atoms. So normally at this point we would form a double bond in order to give boron an octet. But we want to know that boron is one of the exceptions to the octet rule. It is happy to have less than an octet, and this goes for things that are to the left of carbon. So things that have fewer than 4 valence electrons to begin with are fine having less than an octet. Another way to figure out that this is actually the correct structure is, let's draw the other possibility. So let's say we gave chlorine a double bond. Let's do it this way. And then we could compare the formal charges of these structures. So in this top example, remember the formal charge is going to be the number of valence electrons that a single atom would have, so that's 3, minus the number of bonds it's forming, which is 3, and the number of unbonded electrons, which is 0. So right now, boron in here has a formal charge of 0. This boron right over here has a formal charge of 3 minus 4 minus 0. So it's got -1. And we want the formal charge to be as close to 0 as possible. Let's look at it for chlorine. So chlorine atom by itself would have 7 valence electrons, and it has 1 bond and 6 lone dots, okay, unbonded electrons, I should say. So it has a formal charge of 0. In this structure, chlorine, it's 7 minus 2 bonds and 4 non-bonding electrons, so it has a formal charge of +1. So this is not a great structure. This structure right over here is going to be we say it's the dominant structure. Okay, that's going to what will actually form in nature. Okay, let's look down here at some bond length. So we've got 2 molecules, and we're asked about the bond length and bond energy. So let's make sure we draw them out. So N2H4 is going to look like this. And then N2H2 is going to look like this. And I got those by following my Lewis dot steps, which, sorry, I kind of rushed through there, but this is what the structures look like. And so what we should notice is the one on the right has a single bond between the nitrogens. The one on the left has a single bond. The one on the right has a double bond. So as the number of shared electrons increases, the bond length is going to decrease. So like those two atoms are going to be more attracted to each other, so they're going to get closer together. So the one with the longest bond length is going to be the one with the fewest shared electrons. So that would be N2H4. Down here, bond energy, if we look back, as the number of shared electrons increases, the bond length decreases, and the bond energy is going to increase. Because as those atoms share more electrons, they're going to be more attracted. That makes the bond length shorter. It also makes them harder to break apart, which makes the bond energy higher. So the one with the greatest bond energy is going to be the one with the most shared electrons. So that is going to be the one up here on the right, N2H2. Okay, and if we look at one more, let's look at the formal charge down here on these molecules. We're going to use formal charge to figure out which is the better Lewis dot structure. So the way we find formal charge, let's look right here, selenium, is you are going to look at the number of valence electrons a single atom of that element would have. For selenium, that's 6. Look that up on the periodic table. I'm going to subtract for it the number of bonds it is forming, which is 4. And I'm going to subtract from that the number of non-bonding electrons on it, which is 0. So it looks like in this this ion, selenium has a formal charge of +2. If we look at an oxygen atom, a single oxygen atom, would have 6 valence electrons. In this molecule, or ion, I guess, is forming one bond, and it's got 1, 2, 3, 4, 5, 6 non-bonding electrons on it. So it has a formal charge of -1. All of our oxygens looks like are the same, so they all would have a formal charge of -1. Notice our formal charges add up to the overall charge of the molecule. So 2 minus 1 minus 1 minus 1 is -2. Okay, formal charges over here don't look great. We want the formal charge to be close to 0. So right now that's not looking like a great option. Let's look over here and see what this option is. So again, we've got selenium, which by itself would have 6 valence electrons. In this ion, it has 1, 2, 3, 4, 5, 6 bonds and no non-bonding electrons, so it has a formal charge of 0. And then let's look at this oxygen, would normally have 6 valence electrons. It's got 2 bonds and then 1, 2, 3, 4 non-bonding electrons, so it has a formal charge of 0. This oxygen is the same. And then these two oxygens are just like the ones in the structure on the left, so they each have a charge of -1. So the structure that is better is this one over here, because our goal is to minimize formal charge. So if we get the most formal charges closest to 0, that's better. If there has to be a formal charge, you want the negative formal charges to be on the more electronegative element. So in this case, we seem good because oxygen's a more electronegative element. It has a -1 charge, so that's good as well. If we look at number 8, we're looking at, looks like an intermolecular force type question here. We're comparing the melting points of two substances. So it looks like sodium chloride has a greater melting point than hydrogen chloride, and we want to explain why. Well, first step, it's always good to think about what type of bonding is happening in each substance. So if we look at NaCl, it is a metal and a non-metal, so it is held together by ionic bonding. So we're thinking about a lattice with like sodium ions and chloride ions being held together by that Coulombic attraction there. HCl is all nonmetals, and it's not one of our network covalent examples. So that means it has molecular covalent bonding, which means it is held together by IMFs. So the way HCl works is you've got these HCl molecules, and then there are no bonds connecting HCl. Only thing that connects them are these intermolecular forces, which are relatively weak. So and we can be specific about what these IMFs are. The IMFs in HCl are dipole-dipole forces. So there's dipole-dipole IMFs. So the reason why sodium chloride has a much higher melting point than HCl is because sodium chloride is held together by ionic bonding, by this lattice energy, which is much greater than the dipole-dipole intermolecular forces that holds HCl molecules together.